Imagine for a second that an attacker gets into a corporate network.
Right, which happens every day.
Yeah, exactly. And in standard IT, maybe they steal some emails or maybe they hold a financial spreadsheet for a ransom.
Sure, it's a bad day for the company, obviously.
It is. But what happens when that attacker crosses over into the systems controlling, like a city's water filtration plant
Right.
or a regional nuclear power grid?
Well, suddenly we aren't talking about lost data anymore.
No, we are talking about physical explosions, toxic spills, entire cities going dark.
The stakes become entirely physical.
Exactly. And today, we're looking at a source document that holds the blueprint for stopping that exact nightmare scenario.
It's a fascinating read.
It really is. And right on the cover, it's stamped with this marking traffic light protocol white.
Which tells you immediately how this intelligence is meant to be handled.
Right.
Because in the cybersecurity world, the Traffic Light Protocol, or TLP, it basically dictates the flow of intelligence.
Like a color-coded clearance system.
Precisely. If this document were stamped TLP red, we couldn't even be having this conversation right now.
Because red is what, highly restricted?
Yeah, eyes-only intelligence. Sharing it could compromise active investigations or, national security.
Wow. And then there's amber and green.
Right. Amber stays strictly within your own organization. Green can be shared with industry peers, but it has to be kept off the public internet.
But our document today is TLP white, which means the doors are just wide open.
Zero restrictions on sharing this.
Which is fantastic for us, because whether you are watching the video about this OTCC debate or just listening in, we designed this introductory deep dive to break down this dialogue for beginners.
It's a great place to start.
So we are unpacking the Operational Technology Cybersecurity Controls, commonly known as the OTCC 1.2022.
Issued by Saudi Arabia's National Cybersecurity Authority.
Right. And it essentially serves as this master blueprint for defending critical infrastructure from digital attacks.
And we really need to emphasize the difference here. We live in an IT world, but this document targets OT, operational technology.
Right, which is a massive shift.
It is. We're shifting from protecting data on a rack of servers to protecting the literal spinning turbines, the pressure valves, the conveyor belts.
An actual industrial control system.
Exactly, the physical machinery of our infrastructure.
And that physical reality, that is the friction point of this entire deep dive.
It really changes everything.
It does. Because, okay, let's unpack this. If we look at this logically, these industrial systems are ultimately just computers running machinery, right?
At their core, yes.
So I think the immediate question for anyone new to this is, why can't a power plant just install the same off-the-shelf antivirus software we use on our laptops?
That is the most common question people have.
Like, why write a massive, highly specialized rulebook entirely dedicated to operational technology?
Well, the answer lies in three letters that form the absolute backbone of the OTCC.
And those are?
HSE, Health, Safety, and Environment.
Okay, HSE.
Think about the standard operating procedure when your office laptop gets a virus. What do?
You isolate it from the Wi-Fi, maybe shut it down.
Right.
Or if it's really bad, you wipe the hard drive completely and reinstall everything.
The classic IT fix.
Yeah, just pull a plug, wait 10 seconds, and turn it back on.
But if we connect this to the bigger picture, you cannot just reboot a factory pipeline in the middle of a volatile chemical mixing process.
Oh, wow. Yeah, I didn't think about that.
If a standard cybersecurity system randomly decides to shut down a control unit to, say, run a scheduled antivirus scan.
Or apply a random background patch.
Exactly. Then the physical pressure inside a real-world pipe might build up to a catastrophic level.
Because the computer monitoring the safety release valve is suddenly offline doing a software update.
Precisely. IT prioritizes the confidentiality of data above almost everything else.
Right. Keep the secret safe.
But OT prioritizes the continuous availability of the system and the physical safety of the environment.
So, you can't just apply an automatic Windows update to a nuclear reactor at 2 in the morning and cross your fingers.
You really, really can't. The stakes demand a completely different approach to defense.
And the OTCC recognizes that not all facilities carry the same level of risk, right?
Yes. The document categorizes infrastructure into 3 distinct levels: Level 1, Level 2, and Level 3.
L1, L2, and L3.
Right. And the jump between these levels isn't just about adding a few more passwords.
It's more structural than that.
It is a massive qualitative leap in how security is engineered. So, a Level 3 facility is considered low criticality.
Okay, so a breach there might just cause some moderate operational hiccups.
Exactly. But level 1 represents the highest criticality.
The big stuff.
A successful cyber attack at an L1 facility has severe catastrophic consequences to operations, national assets, or even human life.
So the security controls mandated for an L1 facility must be exhaustive.
They are uncompromising. There are 151 separate controls for L1.
Wow, it's structured very much like physical building codes, isn't it?
That's a great way to look at it.
Like, if you are building a wooden tool shed in your backyard, which would be our level 3, you need some basic structural rules.
Sure, keep the rain out.
Make sure the roof is pitched to shed water, use weather-resistant nails, that kind of thing.
Basic common sense.
But if you are constructing a 100-story commercial skyscraper in a major seismic zone, our level 1, a basic toolkit just doesn't cut it.
Not at all.
You are legally required to conduct wind tunnel testing, use specific metallurgical grades of steel.
Install automated fire suppression systems.
Right. The rules scale with the potential fallout of a collapse.
And the OTCC is basically the building code for the digital architecture of that skyscraper.
Okay, that makes perfect sense.
And to ensure those codes are actually followed, the very first domain the document tackles is cybersecurity governance.
Because a 151-point checklist is kind of useless without humans to enforce it.
Exactly. You can buy the most sophisticated firewalls on the market,
Yeah.
but if no specific human being is officially responsible for checking the logs, the technology is useless.
And the document leans heavily on something called a RACI matrix to solve that human element, right?
Yes, the RACI matrix,
Mm.
RACI.
Which stands for responsible, accountable, consulted, and informed.
Right. For every single asset and process in the facility, someone has to have their name attached to one of those letters.
And what's the real goal there? Just assigning blame.
Well, the core mechanism of the RCI matrix in this context is preventing conflicts of interest.
Okay, how so?
The OTCC explicitly demands separation of duties.
Right.
So the engineer whose job it is to implement a security control cannot be the same person evaluating whether that control actually works.
Ah, I see. You cannot grade your own homework when national infrastructure is on the line.
Exactly.
But wait, let me play devil's advocate here for a second.
Go for it.
If I look at this massive list of rules, RCI matrices, separation of duties, mandatory independent audits for every system.
It's a lot of paperwork.
Doesn't this mountain of bureaucracy just completely suffocate the engineers trying to build modern, efficient, smart factories?
That is a very valid concern.
Like, if an energy company wants to implement some cutting-edge automation, having to run every single idea through a massive compliance matrix seems like it would paralyze innovation.
That tension is absolutely real. But what's fascinating here is how the OTCC tackles it.
Okay. Yeah.
By shifting when the security actually happens. It mandates a principle called secure by design.
Secure by design, so baking it in from the start.
Precisely. Security cannot be an afterthought anymore.
How'd it used to work?
Well, in the past, vendors would build a massive industrial system, install it, flip the switch,
And then pray.
basically. And then the cybersecurity team would scramble to wrap firewalls and passwords around it after the fact.
Just slapping Band-Aids on it?
Right. But the OTCCC forbids that. Security requirements must be baked into the engineering blueprints from day one.
So you design the digital defenses at the exact same time you are designing the physical pipe layout.
Yes. And the document gives a fascinating look at how rigorous this gets in practice.
Oh yeah, the part mentioning FAT and SAT, factory acceptance testing and site acceptance testing.
Right. This isn't just checking a box on a form. This is where secure by design gets highly tactical.
Walk me through it. What does that actually look like?
Okay, let's say a facility is purchasing a multi-million-dollar automated turbine.
A massive piece of machinery.
Exactly. Before that turbine is ever packed up and shipped from the manufacturer, the purchasing organization sends their cybersecurity team to the vendor's actual manufacturing floor.
To do the FAT, the factory acceptance test.
Right. They plug into the equipment and actively run penetration tests.
Wait, really? Well, it's still at the factory.
Yes, they try to break the code, flood the network, and inject malware while the machine is still sitting in the vendor's warehouse.
Oh, wow. So they are essentially hacking the machine at the factory that built it.
Exactly. Forcing the vendor to prove the armor holds up before the check even clears.
That is incredible.
And the testing doesn't stop there.
Let me guess, the SAT.
Yes. Once the turbine passes the FAT, gets shipped across the world, and is physically bolted to the floor of the power plant, the organization performs a site acceptance test.
So they run the cybersecurity tests all over again.
They do. because they have to ensure that integrating this new machine into the existing local network hasn't accidentally created a new backdoor.
Or broken some legacy communication protocol.
Exactly.
So the perimeter defenses are incredibly intense.
And it extends to the physical world too, right?
Very much so. The rules around everyday technology are incredibly strict.
Yeah, the OTCC explicitly targets things like mobile devices and external storage.
Yes.
Like you can't just walk onto a level 1 production floor with your personal smartphone in your pocket.
Absolutely not.
Or, grab a random USB drive off a desk to transfer a PDF.
Because in an operational technology environment, a rogue USB drive is basically a weapon.
Right, because it completely bypasses every exterior firewall you've built. Exactly. If someone plugs an infected drive directly into an engineering workstation on the factory floor, the malware is immediately inside the fortress.
Game over.
Pretty much. The physical perimeter and the digital perimeter are just two sides of the same shield.
Okay, so that brings us to the actual architecture of that shield.
Right. Domain 2.
So you've vetted your personnel, you've brutally tested the machines at the factory, and you've banned USB drives.
Check, check, and check.
So how is the internal network actually designed to stop a threat once the plant is running?
Well, the document spends a massive amount of time on network segmentation.
Network segmentation. Here's where it gets really interesting.
It is the tactical core of Domain 2, which covers cybersecurity defense.
Okay.
The OTCC absolutely forbids direct communication between the corporate IT network and the OT network.
The corporate side being where people are checking emails and browsing the web.
Right, and the OT side is where the industrial machines actually operate.
I like to think of it like a VIP medieval castle.
Oh, that's a good analogy.
Like, you can't just stroll from the public marketplace straight into the king's throne room.
Right, you have to go through the gates.
Exactly. The document mandates the use of choke points. You funnel all traffic through specific, highly fortified gates.
And the tactical advantage of a choke point is absolute visibility.
Because if your network has 50 different entry points...
You have to split your monitoring tools and your security personnel 50 ways.
Right. An attacker just needs to find the one door where the guard is asleep.
Exactly.
Go.
But by routing all incoming and outgoing data through a single choke point, you force any potential attacker to walk directly into the teeth of your most sophisticated alarms.
Right into the inspection tools.
Yes.
But the throne room still needs supplies from the town, right?
Says.
Like the factory floor eventually needs the daily production schedule from the corporate office.
Sure.
So how do these two isolated networks actually share data without lowering the drawbridge and exposing the industrial side?
Well, they use a DMZ, a demilitarized zone.
The DMZ.
It acts as a neutral buffer network.
Okay. How does that work in practice?
So if a corporate server has that production schedule, it doesn't send it directly to the factory floor.
Right. Because direct communication is banned.
Exactly. Instead, the corporate server drops the file off in the DMZ.
Like a middle ground.
Yes. Then a machine from the OT side reaches out into the DMZ, inspects the file for malware, verifies its origin, and pulls it inside.
Oh, wow. It's like a digital dead drop.
That's exactly what it is.
The two sides never actually touch each other. They just leave packages in a highly monitored neutral room.
You've got it.
Okay, but what about the human element?
What do you mean?
Like, if an engineer is sitting in the corporate office and they urgently need to remote into a machine on the factory floor to diagnose a mechanical issue,
Okay, sure.
how do they get in? They can't just drop a file on a DMZ for that.
No, they can't. In that case, the OTCC requires them to use a jump host.
A jump host?
This is a dedicated, hardened server sitting inside that DMZ we just talked about.
Okay.
The engineer connects from their corporate laptop to the jump host.
Right.
They authenticate, usually with biometric or multi-factor credentials, and from that moment on, every single keystroke and mouse movement is recorded.
So they are heavily monitored.
Extremely.
Yeah.
Then from the jump host, they initiate a completely new, separate connection down to the factory floor.
So it's a digital airlock.
A perfect way to describe it.
You enter the first door, the door locks behind you.
Right.
You get verified, you effectively change out of your corporate network suit and put on a sterile factory floor suit.
Exactly.
And only then does the inner door open. You are never directly piping your corporate laptop into the industrial control system.
Never. And even with all of those airlocks and dead drops, the OTCC still accounts for the absolute worst-case scenario.
Because no defense is 100% perfect.
Right. So what happens if an attacker actually manages to bypass the DMZ, compromise the jump host, and gain control of the operational network?
The nightmare scenario.
This brings us to the ultimate hardware failsafe. The Safety Instrumented Systems, or SIS.
Okay, the final line of defense.
Yes. If a boiler's pressure gets too high, the SIS is the physical switch that overrides the network and shuts the boiler down before it can explode.
So it's an independent safety valve.
Exactly. The document demands that the SIS be completely isolated from all other OT networks.
So the hacker can't see it.
Right. And more importantly, the controllers for these safety systems must be locked into hardware modes that physically prevent any unauthorized changes over a network.
Wait, physically prevent?
Yes.
So even if a hacker owns the entire digital network, they cannot disable that final safety valve?
No, they can't. Because the physical key on the machine itself is turned to off for network updates.
Oh, wow. You literally have to be standing in the room to change the safety parameters.
It strips the attacker of their ultimate leverage.
That is brilliant.
They can cause a disruption, sure, but the structural isolation prevents them from causing a catastrophic physical event.
Wow. Okay, so you've locked down the perimeter, you've built the DMZs, and you have your physical fail-safes.
Right.
But as we know, a determined, well-funded attacker only needs to be right once.
That's the harsh reality of cybersecurity.
When they inevitably break through that digital drawbridge and bypass the choke points, the entire strategy has to pivot from prevention to pure survival.
Exactly.
So how does a massive power plant stay online while it is actively being hacked?
This is where Domain 3 comes in, cybersecurity resilience.
Okay.
In standard IT, a major ransomware attack often means taking the entire server farm offline.
Right, you just plunge the business into the dark while the backups are restored.
But operational technology cannot do that. The OTCC requires facilities to implement business continuity management plans.
BCM plans.
Right. And these plans must allow the physical plant to operate in an acceptable safe mode.
Acceptable safe mode. What does that look like in practice during a live cyber firefight?
Imagine a chemical refinement facility. The digital monitors that automate the mixing ratios are suddenly blinded by a malware infection.
So the screens go dark.
Right. Instead of the system violently shutting down all the pipes, which could cause a pressure explosion.
Oh, right, the HSE aspect again.
Exactly. The facility degrades its performance to a mechanical baseline.
What does that mean?
The automated digital valves lock into a preset safe position, and the plant shifts to a slow analog operation.
So they just throttle everything down.
Exactly. The throughput might drop to 20% capacity, and human operators might have to run around and manually check pressure gauges.
But the process safely hums along while the cybersecurity response team purges the network.
It buys time. You are limping, but you are still walking.
But managing a transition like that from automated digital control to manual analog control while under active attack, I mean, that sounds incredibly chaotic.
It is.
How do you ensure the staff actually knows what to do when the alarms are blaring?
Well, you test the muscle memory through tabletop exercises, or TTX. The OTCC mandates these simulations regularly.
Honestly, these sound a lot like Dungeons & Dragons campaigns, but for industrial engineers.
You know, the mechanics are surprisingly similar.
Really?
Yeah. The organization locks its executives, plant managers, and cybersecurity responders in a conference room.
Okay.
And a moderator acts as the game master and throws a highly realistic, evolving disaster scenario at them.
Like what?
Like, it's 2:00 a.m. on a Sunday. The main human-machine interface screens just went black. A skull logo appears demanding cryptocurrency.
Oh, wow.
The water filtration pumps are reporting erratic pressure. What is your first move?
That is intense. And the team has to figure out their communication channels right then and there.
Exactly. They have to decide who has the authority to declare an acceptable safe mode.
And just run through their disaster recovery plans in real time.
Right. It exposes the gaps in the plan before a real attacker does.
Which is invaluable.
It really is. It forces them to realize things like, wait, our disaster recovery playbook is saved on the very corporate server that just got locked down by ransomware.
Oh, no! So they learned they need to print hard copies of the procedures.
Exactly. The TTX ensures that when a real incident happens, the response is calculated action, not panic.
Okay, so there is one massive vulnerability we haven't touched on yet.
What's that?
We have trained our internal teams, we have segmented our networks with jump hosts, we have our hardware fail-safes, and we've run our tabletop simulations.
We've done everything right.
Internally, yes.
Hmm.
But what about the folks who actually write the software running inside these machines?
Ah,
Because an organization can build an impenetrable digital fortress, but if the vendor who supplied the control system left a back door in the source code,
the fortress falls from the inside?
exactly, aren't we just inheriting their vulnerabilities?
This raises an important question, and it's the exact reason Domain 4 exists.
Domain 4.
Third-party cybersecurity. Supply chain attacks are one of the most devastating vectors in the modern threat landscape.
Because you cannot build a secure facility using insecure ingredients.
Precisely. The OTCC holds the organization ultimately responsible for the security of its entire supply chain.
But how do you practically enforce that?
It's tough.
Like, a power plant in one country cannot directly control the daily coding practices of a software vendor sitting in a completely different hemisphere.
You can't control their daily operations, true, but you have immense leverage through procurement.
Money talks.
Exactly. The OTCC requires organizations to mandate that their third-party vendors utilize a formal SDLC,
An SDLC, what's that?
a secure development lifecycle.
Meaning the vendor has to legally prove how they build their tools.
Exactly that. Vendors must provide documentation showing they actively search for flaws in their own code.
That they don't use outdated open source libraries, that sort of thing?
Right. And that security is integrated into their software updates.
Okay. But the organization isn't just taking their word for it, right?
No. The rules require periodic cybersecurity assessments and audits of those third-party providers.
So you trust your supply chain to deliver the product, but you verify their security posture continuously before you let their code touch your network.
Trust, but continuously verify.
It is a massive
I
undertaking.
think a huge shift for a lot of companies.
So when we step back and look at everything we've unpacked today, it becomes clear that the OTCC 1.2022 is far more than just a list of technical settings.
It's a holistic ecosystem.
It really is. It bridges human governance with RCI matrices. It demands proactive engineering through secure by design.
It creates tactical digital battlefields using choke points and DMZs.
And it prepares for the worst-case scenario with physical fail-safes and those acceptable safe modes.
It is a comprehensive strategy for keeping the physical world turning securely.
And the urgency of implementing these strategies is only accelerating, isn't it?
Oh, absolutely. We are rapidly moving deeper into the era of the Industrial Internet of Things, or IIT.
Right, the IIoT.
Historically, industrial machines were completely isolated. They just sat in a room.
Right.
Today, sensors, valves, and mechanical motors are increasingly being connected to global networks to optimize efficiency and gather data.
And as that connectivity grows, the attack surface expands massively.
It does. Frameworks like the OTCC are transitioning from being just best practices for a few critical sites to becoming the absolute bedrock of public safety for every connected physical system.
Wow. So I want to leave you with a final thought to ponder today.
Full homework. Yeah.
Exactly. The next time you are driving around your city, take a closer look at the infrastructure you pass.
It's everywhere once you start looking.
It is. When you drive by a water treatment plant, a sprawling manufacturing facility, or even just a local power substation behind a chain link fence, think about what is happening invisibly inside.
All those hidden layers.
Ask yourself, how many digital choke points are filtering traffic right now? How many engineers are authenticating through jump hosts just to check a pressure gauge?
How many defenders are running tabletop exercises?
Exactly. How many unseen defenders are silently auditing supply chains in the digital ether, just to ensure that when you walk into your house tonight and flip a switch, the lights actually come on?
It really makes you appreciate the invisible work going on every day.
It does. We started today by looking at a TLP white document, a public blueprint that reveals the hidden mechanisms keeping the catastrophic red alerts at bay.
A great way to frame it.
Thank you for joining this introductory deep dive into the invisible digital fortresses protecting our physical world. Keep questioning, keep learning, and we will catch you on the next deep dive.